So we are coming to the second lecture. It will be given by Professor Antonio Gens. He obtained his civil engineering degree in 1972 from the Technical University of Madrid, and then his higher degrees from Imperial College. In 1982, he obtained a PhD there, after having been in engineering practice for some years. And since 1983, he has been a faculty member at the Technical University of Catalonia in Barcelona. He's a civil engineer, and he has been involved in geotechnical research, consulting, and teaching for over 35 years. His research interests have notably included unsaturated soils and the development of coupled quantum physics analysis. He has authored or co-authored more than 300 papers published in refereed journals. Professor Gens' scientific achievements didn't go unnoticed. He obtained several awards, among them election to the Academy of Engineering, Royal Academy of Engineering in the UK. He has held several positions in the administration and also in international societies since 2030. He holds the position of Vice President for Europe in the International Society for Soil Mechanics and Geotechnical Engineering. So, Professor Gens, the floor is yours.
I'm going to present some analysis using the discrete element method, or distinct element method as sometimes called, to explore some aspects of plasticity in crushable granular materials. First of all, let me acknowledge my co-authors, Marcos Arroyo and Mateo Chanta. Mateo has done 2 years of postdoc with us, and in fact he is responsible for most of the analysis I'm going to show. This is the outline of the presentation. After introduction, I'm going to present the approach that we use, which we think is quite efficient to model crushable materials, which is a big concern because it's very computationally expensive. Then I'm going to describe the type of analysis we have carried out and to describe some of the results. And if there is time, I would like to highlight some of the microstructural features that you can actually get from this sort of analysis. So it can be said that the story starts in the northwest shelf of Australia, because in the early 80s they developed some gas fields, and one of these platforms, which is still the largest in terms of gas production at the time, the North Rankin A, when they went to install the piles to support these jack platforms, in the first blow, they actually, the pile penetrated the ground for 60 meters. The material was a sand, but it was a calcareous sand, a very crushable sand. And obviously that concentrated mines. The cost of the repairs and the research going into that was over 200 million euros. So these materials obviously are used all over the place. For instance, in these large reclamation projects in warm waters, they're usually calcareous materials. And of course, as I said, there is a lot of research. For instance, these are pile tests in a calibration chamber, and it's can be seen and actually checked experimentally that a large crash zone develops at the tip of the pile, and if you get the grain change distribution before and after, there is obviously a change associated with this crashing. And in fact, even if we go to siliceous sands, which are much stronger, the material, if you go to high enough stresses, like you get at the bottom of a pile, you also get quite a bit of crashing. And for instance, these are the results from some different pile tests. This is done in Grenoble with the Imperial College people, and you can see the evolution of the grain size distribution at different places around the pile due to this crashing. And this is a siliceous sand. So it's been recognized, at least for the last couple of decades, that crashing plays a major role in the behavior of sands and other granular materials. It's important at high stress levels in siliceous sands, but it's important at nearly all stress levels in calcareous sands. Of course, what happens is the modification of the grain size distribution. These are some experiments carried out at City University by Matthew Coop, in which you can see that as you increase the strains, this initially uniform distribution tends towards this final one, which interestingly usually is a fractal with dimensions around 2.5, 2.6. It seems to be pretty universal. Obviously, these changes also change critical state, material compressibility, give rise to instability phenomena, changes permeability, propagation development, etc. So, crashing is an integral part of the constitutive modeling of these materials, which are often based on plasticity. And here there are some references. But sometimes these materials are modeled directly using the discrete element method, which, as you know, is based on the computation of the motion of a large number of finite particles. Here we are not going to use the DEM to look at to check mechanical behavior. Actually, the aim of this exercise is to try to shed light on the sort of suitable continuum constitutive models that can be suitable for these crushable materials. So we have to model crashing in the DEM. There are two major ways of doing that. The first one is the use of multigrain agglomerates, which are formed by different grains, spheres that may break. This has some quite severe disadvantages. First, in terms of computational cost, it's really expensive, but also limited capture of the grain size distribution evolution. The alternative is using the multi-generational approach, in which single elements break and are replaced by a new generation of smaller grains. The disadvantage is the mass may not be conserved, but we will see that eventually this is not as bad as it sounds. Okay, so let me describe briefly the approach that we are using, which is, we think, a quite efficient one. It's been recently published in Geotechnique. First, I'll mention the contact law that we are using, which is an essential part of this method, but then concentrate on two things, the breakage criterion and the splitting configuration. For the contact law, it's a standard Hertz-Milling model. This is the expressions for the stiffness, normal stiffness, sliding stiffness, and the evolution of the radius as you increase the force. So this is pretty standard, but these are the actual contact that we use. For the breakage criterion, there's been many proposals, but we like especially, we adopted one which can be traced back to Russell and Booth, work back in 2009. Basically, they use a two-parameter strength for the material forming the particle, which are related to compression and tension strength, and they check the elastic distribution and the point load, and eventually generalize to several loads, and identify the most stress point, and when this point gets to the value of the strength of the material, then we get breakage. So this computation gives rise to this expression, which actually can be grouped in two parts. This first part is a stress, which depends only on the properties of the material itself, the material forming the particle. So this is a kind of limit stress. And the second part it refers to the contact failure area for this particular case. So it's the product of these two which actually give us the criterion to check whether a particle will break or not. Obviously, we know that there is a size effect in the strength of particles, so we assume that there is a Weibull-like dependency of this strength, which is expressed this here. The basic parameter is this exponent m, and also we assume that there is some variability even for the particles of the same size, but here we use just a normal distribution, which is actually supported by experiments by choosing the correct variance. in fact, because crashing is very topical, there's been quite a number of single particle tests that can be used to try to calibrate these models, in which we relate the limit force that causes the breakage and the size of the particle. And we can see a number coming from different authors and different materials, and we see that a value of m around 10 for the Weibull distribution actually gives a quite reasonable representation of the experimental results. The second important thing is how we split the particle. And to do that, we use the Apollonian spherical packing because it's reproducible. You can get as many spheres as you want. And it also has the nice property that the actual fractal number, this is a fractal, is 2.47 whatever, so very close to the 2.5 typical of the degrading of the sun. So we have the parent particle, and it's replaced by a number of daughter particles which are inscribed inside, maybe 2, 3, 4, etc., up to 57 or more. Of course, there is some mass loss when you do that, and this mass loss actually reduces with the number of particles. But in fact, the fact that this mass loss, the fact is that these finer particles, they don't contribute very much to the overall mechanical behavior, because it's well known since the last 3 decades that the resistance in these granular materials is actually through a series of force change that go mainly through the largest particles forming these columns. So we are going to assume that the mass loss is a fine particle which don't contribute to the mechanical behavior, so we are not going to consider it in the mechanical analysis, but certainly we are going to consider it for the evolution of the grain size distribution. And here we make the assumption that this fine fraction has a fractal dimension of 2.5, so it has this distribution, and is included in the ground size distribution. Okay. An important thing is the orientation of these daughter particles. It's been found in experiments that usually the breakage in a particle propagates in the direction of the applied force. So we are doing that. When we reach the limit force, then we orient the largest particles, the largest daughter particles, in the direction of the force that has caused the breakage. And this is also part of the formulation. How does it work? Well, you can look at the geotechnique paper. There are many examples there that shows that not only is efficient, but also quite realistic. One thing important is how many daughter particles that we use. Here there is a simulation of an odometer test. This is vertical strain versus applied stress, and we can see that there are variations as we increase the number of particles from 2 to 8, 14, but once we get to 14, there is not much more happening. The same for the grain size distribution. So we consider that a 14 daughter distribution, a splitting of the original particle, should be enough to give us a good result. And that's what we are going to use in all the analyses I'm going to show. As I said, we have several examples that the things seem to work well, and just giving one. This is on material called petroleum coke, which is very crushable. There are quite a number of experimental results. Here is an odometer test, and we can see that this is the experimental results, that this DEM analysis actually follows well these changes in volume. If we don't use crushing, obviously the thing is totally unrealistic. And not only at this level, also at the level of grain size distribution is quite closely modeled by this way of actually, by this procedure. We can see here that we go to very large strains in this particular case, just for showing. Here we have 2 cases with different scales, but they give the same result. It's a scalable procedure, but they don't have time to get into that. And we can see that from this original height, we go to nearly a half. The colored balls are the ones which are new generation of balls, which are a product of the breakage of the original particles and so on. So it's quite a robust scheme and quite realistic one. Anyway, what sort of analysis I'm going to perform? For this presentation, I've chosen to use this probe analysis, in which it's a very special kind of tests which are very discriminating with respect of the sort of constitutive model that is applicable to a particular material. The idea is that we go to a common point, and at this point we do different tests on different samples, obviously, in which we apply a small increment of stress in different directions. We check the strains, and that's our response envelope. This has been done experimentally, but it's very difficult to get always the same sample at this point, and then the strains are very small, difficult to measure. There are time effects that affect the results, so they are difficult to do, but they are not that difficult to do, obviously, if you represent the granular material in the computer. And that was done some time ago by Calvetti, Tamagnini, and co-workers. Here, what we are going to introduce, and this is new, is the fact that the particles are crushable. So we are going to stick to triaxial axisymmetric stress conditions, because that's very common in some mechanics. So we have a vertical stress and horizontal stress which is the same in all directions. Often the deviator stress represented by the Q, mean stress by P, and this ratio between Q and P is called the stress ratio. Anyway, we are going to apply stress probes in different directions. In order that they have the same magnitude, they will plot as a circle if you use this, what is called the Rendulic plane, increment of vertical stress and square 2 of the radial stress. And I'm going to characterize the orientation by this angle here. So 90 degrees corresponds to triaxial compression, 0 to radial compression, isotropic compression would come around here, deviatory compression here, and so on. And as a result, I'm going to measure strains. I'm going to obtain a strain envelope that I plot on the same sort of Rendulic plane, vertical strains, increment of vertical strains, square root of 2 increment of radial strains. And let's see how it goes. I'm going to look at it in the framework of plasticity. So if we do some undergraduate plasticity, basically the magnitude of the stress is proportional to the scalar product of the increment of stress and the normal to the yield surface. So you would expect a magnitude of plastic strain like that, like this is a cosine, like that. And also, according to the same basic plasticity, we would have a unique direction of plastic strains independent on the direction of the applied stress. So if we do the probes, we should obtain something like that. Of course, if things are more complicated, for instance, if you have a double mechanism, double yield surface, then you have to add them all, and you have a transition between the two orientation of plastic strains. If you have a generalized plasticity, if we assume the same hardening modulus in both directions, you get something like that, and etc. So let's see what we obtain. This is the analysis. They were done in these cubes, which are loaded by what is called walls, basically platens, that are smooth. So what we are applying are principal stresses and measuring principal strains. We check different number of particles. We found that 10,000 particles was enough to get repeatable results and representative results. The material was calibrated to represent Fontainebleau sun, so it was calibrated using triaxial test, odometer test, and some basic particle material parameters. So these are the parameters. There are not many. In fact, there are 6 because these relate to the size of the particles. These 3 parameters represent the contact parameters, and these other 3 represent the variation of strength with particle size. So that's all that has to be determined. We are in a small strain plasticity. We assume that the thing is additive, so the total strain is elastic plus plastic. But the plastic strain has now 2 components, hopefully. One, which we call structural, which is related to the change of the fabric, of the structure of the material, of the position of the grains, and this one due to crushing events. So this is the final expression. So what we are going to do is stress probes, a small one, 1% of the maximum applied load, space 10 degrees, And in each probe, that's what we need, an efficient method, we are going to use 3 analyses. One is elastic, so we don't allow any plastic-induced mechanism, so there is no sliding, no crashing. That should give us the elastic strains. Elastoplastic, with no crashing is allowed, so we get the structural component of the plastic strains, and elastoplastic with crashing, we get the full load. By comparing these 3, we can identify the individual strain components. So let's see some typical results. This is for a Q equals P equals to 52 megapascals. This is the elastic response envelope. It's always an ellipse, and we obtain it. And when we introduce sliding, we get this. And if we subtract one from the other, we get the plastic strains. And the plastic strains are in a single line, so we have a single orientation independent of the stress probe orientation. If you look at the magnitude, and the value is 124 degrees. If you look at the magnitude, it just follows the expected cosine, so things work beautifully, and that's what had already been observed in previous works. And here we have that the normal to the yield surface is 150 degrees. So it's not associated, not very far, but it's a non-associated plasticity. So in this respect, it's a very simple, it points to a very simple model, at least at this level. Now, if we add crashing, we get higher strains. And again, if we identify the plastic strains due to crashing, we have, again, a single direction, slightly different from the previous one, and we also have this sort of cosine distribution. It's a bit more unstable because when you have crashing and there is a crashing event, sometimes there are cascading events, so you have to play a bit with the damping parameters to get something reasonable. But we can see that by and large is also. So putting here all together, the strain envelopes, the direction of the plastic strains, and the overall plastic strain is the sum of the 2 mechanisms, which in this case they are not too separate, very much separate between them. So we can, we had also a parallel work, which I don't have to do the time to show, in which we apply deviatoric probes. So we move in the deviatoric plane, increment the mean stress is equal to 0. This is here is the direction depends on the load angle. We can see that these are the strain envelopes, and what we find is that something that which has been found both experimentally and numerically, that now the orientation of the structural plastic strain depends on the orientation of the increment of stress. This is different from what before, but not for the crashing events. So we can see that there is this variation, which is not accounted for in normal plasticity. Now I'm going to explore some radial stress path. First of all, I have to define something which is called the grading index. When we have a current grain distribution like this, we can define how close we are to the final fractal one by just computing this area A over the total area A plus B. So when we are 1, we reach the final situation. So here we actually had different, that has moved, should be up there. We have different values of eta, and we stop at different points, and we can track what's this gradient index as we keep more and more crashing as we increase the stress. And I'm going to use to look at this value of gradient index, 0.8, in order to be compared to see the effect of how far we are from failure on what we observe. And here we can see these 4 results from these 4 cases. Here there is no plasticity, there is a bit of crashing, but nothing similar. Again, for eta 0.3, a bit of crashing, nothing much. We have to get much closer to failure in order to start finding significant plastic strains and significant crashing events. And we got to eta equals 1, well, we can see that these plastic mechanisms are working very hard. So there is not much to say about when we are far from failure, but we can see when we compare all these results that there is an evolution on the orientation of the yield surface, there is an evolution in the value of the orientation of the plastic strains as we move towards failure. But in any case, the overall behavior can be simply modeled by the superposition of these two mechanisms. Another thing which are always interesting in solid mechanics is stress path dependency. So very quickly, we come here to this common point through three different stress paths. A radial one, this is the results I was showing at the beginning, a triaxial compression path, and a constant P path. And we are going to compare the results. Here are the stress envelopes, strain envelopes. You can see that the orientations look very much the same. We are going to confirm that. And the magnitudes are higher here than in this one here. But when I compare angles, we find that both the angle of the yield surface and the angle of the plastic strains are the same in all three cases. So although there is some effect on the magnitude of the previous stress path, there doesn't seem to be any effect on the orientation of yield surfaces and plastic potential at this point. Okay, just to finish, there will be a lot to say about microstructural observations. I'm just going to show one case, which corresponds to this case in which we went to this point through the triaxial, but they are all similar. This is the response envelope. I'm choosing this orientation, 130 degrees, which correspond to this point here and this other point here. And here, what is plotted are the normal and shear forces at each contact. In the initial one, after applying in the elastic case, elastoplastic case plus crushing. We can see this is obviously the limit strength. It cannot go above that. When we apply elastically, we go above that, as we can see here. It's not a very good plot to see that. I'm going to show it in another way. But of course, this has to be dissipated away when we introduce sliding and crushing, and everything goes back below the limit, the limit condition. That's another way to plot the same results. This is the normal stress. This is the tangential stress over normal stress times the friction. So when this is 1, we reach failure. So we can see when we apply the things elastically, there is quite a number of contacts that go above what is permissible. It's a kind of elastic overstress. When we introduce the sliding, it goes back to this. To this distribution of contacts, and when we introduce crushing, it changes. It's not easy to see how it changes. Perhaps it's easier to see it here. You can see that there is a variation between red and blue. And it's also interesting to look at the orientation. Here we are plotting the normal force, but plotting also the orientation. Here the orientation 0 corresponds to the contact in the wall, which is not relevant. Basically, they are oriented around, most of them, in 30 degrees, 150 degrees, which is typical of a sample on which we have applied vertical stress. And if I look at the contacts that are going to be involved in crushing, which are here, we can see that there is a much more isotropic sort of distribution. So, and I finish, this is, can be related to macrostructural observations. Here is, again, the direction of plastic strains. The red one are the structural ones due to the reorganization of the fabric. The black ones are the ones due to crushing for all these radial path samples that we tested. And we can see that every time, everywhere, when the two are present, the amount of volumetric strain is higher in the crushing event than in the sliding fabric change mechanism. And we tend to think that this is related to this more isotropic distribution of the crushing events. So let me conclude that we have carried out a stress profile analysis, which have been performed on a virtual sample of crushable granular material using DEM, and it's been essential to apply this new procedure, which allows a much more efficient modeling of these events, and quite realistic too. We have seen the structure, that is the plastic strains without crushing, appears to correspond very closely to the predictions of a single mechanism of non-associated plasticity. This perhaps explains why these sort of models are so much popular in geotechnics and soil mechanics. When we incorporate crushing, then the overall behavior is well modeled by a two-mechanism non-associated plasticity. Of course, crushing behavior is more unstable, so the corresponder is not so close, but close enough for practical purposes. And when we apply deviatoric probes in contract, we are not so close to the classical plasticity postulates, because now the direction of plastic structural strengths depend on the orientation of the stress probes, but not the crushing ones, which is again another interesting observation. We found that the magnitude of these plastic strengths very much depend on the deviatoric stress level, and the closer we are to failure, the more significant they are. And the previous stress path appears to affect only the magnitude, but not the orientation of the angles of the normals to the yield surface and plastic potential. And finally, we didn't have time to develop that in detail, but microstructural observations does contribute to a better understanding of macroscopic results. There is a wealth of information there that helps to understand why these apparently macroscopic continuum models seem to be working well for assembly of granular materials. Particle crushing appears to be more associated to an isotropic distribution of events, although we have to confirm that looking more closely at the results, but it certainly seems to be related to the fact that it gives a higher ratio of volumetric strains. And this is all. Thank you for your attention.